Good morning, students.
Good morning, sir. Good morning,
Good
sir.
morning, sir.
See, you are supposed to make formula notes of this chapter, okay, on one page. Write the topics and then the formula notes on it. That's very important. So, what we have studied in this chapter, like we started with, what we have started with? The like two kinds of motion, pure translational, pure rotational, and then rolling motion, right? So our chapter started, the first topic that there was in our chapter was 7.1. So in 7.1 we studied pure translation, pure translational motion, pure rotational motion, and then rolling motion, which is translational plus rotational. Okay, and then the last topic of the chapter, which was 7.14, was also this, where we have found the kinetic energy of the body rolling down, and that we have found, we can write it as the kinetic energy due to rotational motion and kinetic energy due to translational motion. So due to rotational motion, it is half I omega square. So simply, like we know that K is equals to half mv square. So in the place of m we have moment of inertia, and velocity, linear velocity, we have angular velocity. So that's rotational kinetic energy, and now translational kinetic energy. So translational kinetic energy is the velocity of the center of mass. So we can write it as either v center of mass square. We can write it like this, or we can write it half m. So here also small m we need to write. We are assuming that the mass of the whole body is concentrated at this point, which is your center of mass. So mass of the body. So if I'm writing its velocity, I will write it capital F, and I can, if I'm using small m, I can write VCM. Then I have to mention VCM, the center of mass. Otherwise, capital V. So both ways I can write. So that's the formula that we derived for the kinetic energy pure translational motion. We know that the velocity of all the particles of the body, so particles have same velocity at instant. We have figure 7.1 also for this, figure 7.1, figure 7.2 for the rolling motion, and for the pure rotation motion we have figure 7.3. So particles have same velocity at time t, and here in rotation motion particles have same angular velocity at time t. Then 7.2 topic we studied center of mass. So center of mass we have just discussed, that is the body, and suppose I am applying force on this body. So different particles have different acceleration and different velocity. So whose acceleration and velocity we are going to study? So this is C, center of mass. So we assume that the whole mass of this body is concentrated at this point, and when I apply the force, then the force will be applied on this point, and I'm going to study the velocity. So writing it with capital V and capital A, velocity and acceleration of this center of mass. So that center of mass where the whole mass is concentrated and all the external forces are applied at that point. So for the center of mass, whole mass of the extended body or of the system is concentrated, and then all external forces are applied at that point. So all external forces, sum of external forces applied at center of mass. And then third point, we study due to it, we study the velocity and acceleration of center of mass. Okay. Then we studied how to calculate center of mass, formulas for calculating center of mass. So this, like, we studied it for two particle system. So the two particles M1, M2, and they lie on the same line. So suppose this is our origin, and this distance is x1 and this distance is x2. So obviously center mass will lie somewhere between M1 and M2, and it is at a distance capital X. So that X can be written as center of mass, the position of the center of mass, x1 m1 plus x2 m2 divided by m1 plus m2. Now we did one example also, means exercise question 7.2 I think, so where we were supposed to find the center of mass of HCl molecule, but there you see we took the origin at m1. So while doing the calculations, we take one of the mass at m1, so that easy for us so that at least one of the variable like x1 will become a 0. So that's important thing that you need to see. So the only distance I left with, this distance is x2. I can write it as x, and the center of mass will lie somewhere here, so that's distance x. So there. So now in this formula, when this is the case, then this will cancel out x1. So I'm left with, and this x2 has become x into, and its mass is m2. So x into m2 divided by m1 plus m2. Okay. And if the two masses are same, suppose here if the two masses are same, then I can write x1m plus x2m divided by m plus m. So this m will cancel out, and I get x1 plus x2 divided by 2. So if I have a rod, so then the center of mass will be exactly at the geometric center of the rod, at the midpoint of the rod. So that was our exercise question 7.1, that where are the center of masses of these bodies. So if the bodies are symmetric, then the center of masses will lie at the geometric centers of the bodies. Okay, so we find some center of masses of some bodies, and in example 7.1, 7.2, 7.3, and then we studied the motion of the center of mass in topic 7.3, and we derived some formulas, and the formula that we were talking about, the net external force, results into the motion of the center of mass. So these capital letters I am writing because I am writing this equation for center of mass. And then we studied the linear momentum of the system of particles, topic 7.4, and then we have written it for the center of mass, that if the rate of change of center of mass is depends on the force. So same formula that we used earlier, and if this is equals to 0, if no external force is applied, then the momentum is conserved, momentum is constant, momentum will not change. So same formula as Newton's second law we have extended here. And after that, in next topic we studied was 7.5, that is vector product. So vector product, we studied that if there's this A, then B, and let it be A, let it be B. So this is vector A, this is vector B. Now A cross B, put your fingers of right hand, so fingers and thumb should make an angle 90 degree, and put your hands fingers on A and rotate them towards B, so your thumb will point the direction of A cross B, and that is the magnitude of this vector A cross B, and this distance is this length is, it's like this length was your A, this length was your B, and this length will be your A cross B magnitude. So that's the direction. So isn't it? That's how we draw the vector. The length is the magnitude and this is the direction. So A cross B is A, magnitude of A into magnitude of B into sine of angle between them. That's the magnitude, and n cap with the vector direction, unit vector, we are multiplying. Now one more thing is that this A cross B is equals to half of the area of triangle contained by these vectors. As this was your vector A, and this is your vector B. So that was exercise question 7.3 that we did yesterday. So that's the area. So the magnitude of the of course area is magnitude. So area of half of the area of this triangle, we know area of triangle half into base into height. So we calculated it yesterday. We found that this is angle theta. So this height was B sine theta. So the base was A. So half into base was A and height was B sine theta. And AB sine theta is nothing but the magnitude of the A cross B. So half into magnitude of A cross B, that is your area. So area is half of the magnitude of the cross product. And now we can, if we extend this from triangle to parallelogram, so of course this A cross B is nothing but the area of this parallelogram. The magnitude of A cross B is equals to area of parallelogram. Okay, so and then where is the direction? This is the magnitude. The direction is perpendicular to the base containing vector A and B. So that's the perpendicular. So that's n cap. And so here also you can draw this. So at some places, students, you will find the direction drawn here also, and at here also. In physics we draw the direction here also. So you'll find that this is your base area, and what is the direction of this area? See, in 12th class we'll study that area we can also consider as a vector. Okay, area is a scalar, but when there is something passing through this area, like field lines passing through this area, So we start considering it as vector, and what is the direction of this area? So that's the direction of this area, that is vector. So same case here, that this is area of parallelogram, and then the direction is this. So something like that we do. So we draw the direction here also and here also. So, and then we have, suppose, one more vector, that is vector C. So we studied the scalar product, that the volume of the parallelepiped is equal to the scalar product, that is A dot B cross C. It is there in yesterday's video. So we extended further this to volume also, volume of parallelepiped. Then next topic we did was angular velocity, and angular velocity we found that v is equals to omega cross r, and we can write v is equals to r omega, and omega is equals to v by r. So this formula we have studied in the chapter 4 also, so studied here also. And of the angular velocity we know that is also theta by t, and if this theta is full one revolution, that is this means the full angle 2 pi radian upon time of the revolution, that is the time period is 1 for one revolution is capital T time period. So that can further be written as omega is equals to, so this is angular velocity, and this omega is equals to 2 pi, 1 by t is frequency, that is nu. So I can also write it like this. So now this has become, so now you are writing the omega in terms of frequency. So this formula has become the formula of angular frequency. So after that we studied the next topic, that was and we derived the formula like for we written the formula for angular acceleration also, like we have acceleration that is dv by dt. So here the angular acceleration is alpha is equals to d omega by dt. That's the instantaneous acceleration in linear motion, and instantaneous acceleration is, this is angular acceleration in rotational motion. Then we studied topic 7.7, that was torque and angular momentum. So torque and angular momentum. So like we are studying that means we have replaced this velocity with omega, acceleration with alpha. So what the force, rotational part of the force? So this is rotational motion, this is linear motion. So variables are changing. So here this is tau. Okay. So the role of force is played by tau. Here we have angular linear momentum. Here we have angular momentum. Okay. So and we have only 3 cross product that we get from here. So only 3 cross product. One I have written already, v is equals to omega cross r, and the second one is tau is equals to r. So it starts with r. They start with omega. So r cross f, and this L is equals to angular momentum is equals to linear moment r cross linear. So both this formula they start with r. Remember this thing. This I can further write as the magnitude of this tau can be written as RF. So because this is RF sin theta, the magnitude, and r sin theta will be a perpendicular component of the r, and L can be written as r perpendicular into P, and V can also be written as r perpendicular into omega. So these are the magnitudes That's how we can write them. So this is the simple. So torque, we can also call it moment of force. Angular momentum, I also call it momentum. So means moment of linear momentum. And we studied these formulas. And then we studied the next topic, 7.8, equilibrium of rigid body. So now, as we are studying two kind of motion, linear and rotational, so equilibrium of rigid body means this linear means translational motion. So translational equilibrium as well as rotational equilibrium. So you can see translational equilibrium can only be there, suppose I have forces along the x-axis and y-axis. So when the net forces along the x-axis is 0 and net forces along the y-direction is 0, and if there is z-axis also, then the forces along the z-axis are also 0, then it is a translational equilibrium that we have already studied, right, in chapter number 4 or chapter number 5. Which chapter? So that we studied in chapter number 5, right, this equilibrium, and that was on page 99, topic 5.8. So this was topic 5.8, page 99 of NCERT, translational equilibrium. So equilibrium of the particle. Okay. Now we have rotational equilibrium. So similarly here, the net force was 0. So here also in rotational equilibrium we need net torque to be 0. Okay. So then we will have no rotational motion. So this is so on the basis of this we are going to do the exercise questions today. So we have the questions that we are going to do today is question number we have done the questions up to exercise 7.6 yesterday, so we will be continuing with the questions 7.7. If you have not if you want to see the solution, you can see the last video. Now exercise question, exercise 7.7, page 178. So students, read this question, open your NCERT book. 2.7 also we did, so we will be doing 7.8, which is based on this equilibrium of the rigid bodies. Okay. So you can see that there is a figure of this question 7.8. So that's our question. So we have a non-uniform bar. So students, that is important. The bar is not uniform. Okay. So bar is not uniform. Okay, so after doing the topic 7.8, still in 7.8 we have another topic, that is center of gravity. So what is this center of gravity? Center of gravity is the point where total gravitational torque of the body is zero. Where this total gravitational torque of the body is zero. That point is center of gravity. So it means at this point, suppose this is the body, and so we have figure 7.24. So this is our body, and this is the point G. So that's the center of gravity. So at this point, this sum of all the torque which is acting on this body is zero. See, if you lift your notebook from your finger, from at any point, it will rotate first and then fall down. You can check it out. It will tilt on one side, so that tilting is rotation. And then it will fall down. So, but if you hold your notebook with your finger at center of gravity, then it will not tilt, it will balance. So not tilting, not balancing, not rotating, it means it is not rotating. So it means that the total gravitational torque on the body is zero if it is balanced. So it is not tilting, it is balanced. So so it is in rotational equilibrium. So that point where you are holding the body and body is not rotating, so it is in rotational equilibrium, that point is a center of gravity. Okay, so if you want to hold a body, so means if you want to pick a body and want it in rotational equilibrium, so then you have to apply the same force here. Okay, so the force gravitational force applied by this body at G is that force is mg, of course. So m is the mass of the body. Okay, so m is the mass of the body, and at this point, so you can assume that the whole gravitational force is added up at this point. So m is the mass of this body, so m into g. So if you want to pick it up, so then means you have to apply the force with your finger or hand, and then that will be the reaction. So R will be equals to mg. Okay, so body is applied the force on your finger, and your finger is applying the force back. So this is the force which is applied by the finger, R, reaction. Okay, so center of gravity. So here also, so that's equals to the weight of the body. So whole weight of the body is, so we have found a point. So otherwise this point has mass m1, and it is a downward force acting on it is mg1, mg2, but we need not to write the separately. We have one point, and if the gravitational force is same, throughout the body, then gravitational, so if G is constant, uniform, then center of gravity is the same point as center of mass. So these two are different concepts. Center of mass means and center of gravity, but yes, they are coincident if G is constant. So here the concept is that it is non-uniform bar. So bar is not uniform. If it were a uniform bar, then of course at the midpoint we will have this whole weight. So the center of gravity will be at the midpoint, but this is not uniform bar. Non-uniform bar means center of gravity is not at the geometric center, and it is suspended at rest by two strings. So these are the two strings that we have. The angles made by the strings with the vertical are 36.9 degree and 53.1 degree respectively. The bar is 2 meters long. Calculate the distance d of the center of gravity of the bar from its left end. So this is the right end, this is the left end. So this distance we are supposed to find. So what is this distance? Okay, understood this question? Now, what are the forces? So we have to calculate the forces which are acting on this bar. See, this string has tension force. This look at this string, this half part, like this is pulling this rod and the rod is pulling the string. Okay, so the rod is so we will have the tension force. So where will we have where this what the string is doing? The string is, is pulling this rod. So this way. So here it is pulling this it is tied over here. So it is pulling this wall or whatever is, and the tension force from here will be in this direction. And you can see that the net tension force in the string is 0. That is why there is no movement, or string is not broken down. So here this effect we are concerned with this part of the string. So we have the tension up. So this is the tension. We can let it be T1. So you have seen here that we have to derive all the components. If there is some force which is not along x-axis and y-axis, we have to bring it on the x-axis and y-axis. So we need to find its x component, y component, and then we are going to adding them up along the x-axis and y-axis. That's our target. Okay. So what's this angle? If this is 36.9, we have so here this tension is suppose T2. So this length is T2, okay, and this T1 is if you are considering it up to here. So then this is the direction and the magnitude of this T1, and let us resolve it into components. So this will be the horizontal component and this will be its vertical component. Similarly here it's vertical component and its horizontal component. So let this angle be theta and this angle be phi. So this component you can see will be T1. So this length will be opposite side, so T1 cos theta, and this is adjacent side to theta, so T1. So opposite is T1. If you are considering this angle as theta, like they will be the corresponding angles. So let us take this angle as theta, then this will be opposite side, so this opposite will be T1 cos theta, and this side will be the adjacent. So this will be this vector will be T1 sin theta. Okay, you can take it like this also. That's your choice, which one you want to take. So if you look at SL order, so solution which is there on page 7.70. So he has taken so this is theta, so this angle is also theta, this angle theta, this also theta, okay, and this angle and these are alternate angles. So let us draw it in the same way as it is drawn in SLRI. So anyway you can draw, students, you will get the same answer. So I am drawing it so that this theta will not change. So this is my tension T1, and I am resolving it into x and y components. So this is adjacent, so this length will be T1 cos theta see, we have the formula open, Adam open, hurry, Adam. So sine cos tan. So opposite side is equal to sine hypotenuse sine theta, and adjacent side is equal to hypotenuse cos theta. So we need not to get confused here. So this is T1, and if we are assuming this angle as theta, so this is the adjacent side to theta, so this will be T1 cos theta. This side is this length is hypotenuse sine theta, so that's T1 sine theta, so T1 sine theta. You can draw them separately here also. Okay, similarly here, so we will have T2 sine, so we are assuming this angle as alpha, phi, this angle we were treating as theta. So T2 sine phi, this is your phi, and this is, so again, so this was your T2, resolving T2 into components, T2 sine phi, T2 cos phi. Okay, now translational equilibrium. So we have resolved the forces along x and y axis. So simply we need to add, see, summation of all the forces along y axis is 0, summation of forces all along x axis is 0. So you can take so what are the forces along x-axis? So this direction as positive and this direction as negative, upward direction as positive, downward direction as negative. So let us write for x and y. So for x we have so what are the forces? So this one is negative minus T1 sine phi. This is this positive, so this is T2 sine phi, positive direction, and then this is positive direction, and this one is negative direction, T1 sine theta. So then net is okay, this so the net is 0. Yes, fine. Only two forces are there. Now along y-axis we have three forces, two upward and one downward. So T1 cos theta upward, positive, plus T2 cos phi upward, positive, and then W is downward, so it will be negative. So students, you will face these kind of equations where the net will be 0. So like in 12th class also we will have this kind of equations. So where means one direction is positive, one direction is negative. There is one more way, one more way in the sense that from this equation what you will get? You will get T2 sine phi is equals to T1 sine phi, sine theta, sorry, and T1 cos theta plus T2 cos phi is equals to, this negative will become positive coming. So you can see that this is the T2 sine phi is the forces towards along the positive x-axis, and this is along the negative x-axis. So equate them. If it is in equilibrium, so you need not to concerned about this sign. So you can simply write forces on the right hand side along the x-axis is equal to forces on the left hand side towards the left. Forces towards the right is equal to forces towards the left. And here also upward forces along the y-axis, upward forces is equals to downward force. Then only it will be in equilibrium. So you can directly start with this also, so that you will have this kind of situation in physics at more places also. So here I think this is a better way, because you are not going to get into sign conventions. Okay, but some of the time to solve the equations we need to bring this into this side, so it will become negative. So it depends what you need to solve the equation. Okay, now rotational equilibrium. So in rotational equilibrium, net tau is equals to 0. So if this is your rod, and we have the forces, this is T1, this is T2, and this was the weight. So you know the formula of torque is equals to R cross F, and the magnitude is RF sine theta. And you know this R sine theta is actually the perpendicular distance. So what's this perpendicular distance if we calculate? Students, this is a rod, and suppose I am applying the force here in this direction. Okay, and this is the point where I am applying the force. So this is my O, this is point A. See, this rod will rotate like this, okay, in this direction, because force is acting in this direction. So where will the rod rotate? Of course, it will rotate in this direction, that is anti-clockwise direction. So we have only two possibilities. If I apply force on the downward, anywhere, like here or here or here, anywhere on the downside, it will rotate clockwise. If I apply force anywhere on the upper side, whatever be the direction of the force, so it will rotate anti-clockwise. Okay, so I'm taking this particular case. Of course, this will be the rotation, the rod will rotate in the anti-clockwise direction. So what is this R perpendicular? What is this R sine theta? Let us do it. So this is my vector R. This is the vector R, position vector of the point where you are applying the force. So you are applying the force at this point A. So this is a position vector from the origin. So origin I have taken as axis of rotation is passing through this point, perpendicular to the plane of this screen. The axis of rotation. Now, angle between R and F. So this is the direction of R. This is the direction of R, and this is F. So this angle will be theta. The angle between direction of R and direction of F. And what is the direction of tau? Put your fingers on this direction R, direction of R, and rotate them towards F. So your thumb will point out of the screen. So the direction of torque here is out of the screen. So you will see the arrow coming out. So this dot and in the circle. So that's the direction of torque coming out of the plane of the paper, and whose magnitude will be RF sine theta. So this magnitude is R. This magnitude is F. So now student, you have got what is R vector, this R vector, and its magnitude, of course, this is R. Now this is F vector, and its magnitude is F. And this is theta, the angle between the direction of R and direction of F. So now you can find this sine theta. So this R sine theta. Now this next thing is that this force, this I call line of action. So what is this R perpendicular? How will you get R sine theta? See, this is theta, vertically opposite angle. This is also theta, this angle is also theta, vertically opposite angles. So that's theta, and this also theta. Now you have to, now this is your r. Of course you have means you need to make this r hypotenuse. So how can you make this hypotenuse when the opposite angle is 90 degrees? So draw a perpendicular over here. So that's the perpendicular, and we have just said that the opposite side is equals to hypotenuse sine theta. So that the side opposite to theta, this hypotenuse, this is this adjacent side, this is opposite side, this side is opposite side. So this is r sine theta. So I also call it r perpendicular. So r sine theta is r perpendicular. This is the meaning of r sine theta. So how is it perpendicular? So what is perpendicular? So perpendicular means the distance between. So this difference between r and r perpendicular. R perpendicular is your r sine theta, and that is the distance between your axis of rotation and line of action. Axis of rotation and line of action. So students, the distance between axis and this line of action, this is a line of action, and this is your axis of rotation passing through this point. So that is your r perpendicular, and this r is the distance between origin means axis and the point where force is applied. So I have explained you all the variables, and I've told you that there are only two possible moments about O. One is this clockwise, and if the force acting on it is in downward direction, so then this will be the direction of the motion. And if the force is applied anywhere on the upside, so then this will be the direction of motion. This is your axis you are considering. So this direction. So here also, like in translation motion, we have two directions, positive and negative. Here also we have to take these two directions. So this direction I can take as anti-clockwise as positive, and this clockwise as a negative direction. Okay. So now let us write the torque equations for this. So for rotational motion, for rotational equilibrium, so students, the important thing is that the formula is tau is equals to r cross f. So tau will be there for all the f. So how many f you have? How many forces you have? 1, 2, 3. So we will have torque for all three of them. Now, like we did in the case of center of mass, we can take this distance r as 0. Take the origin so that at least maximum r will be 0. So if r is 0, then torque will be 0. Okay. So let us take the axis of rotation passing through this point, so that at least at this point you will have the torque as a 0. Is it okay? And this distance we can write as d1, and this distance from origin we can write as t2. So this is the axis of rotation. So moments about O we are going to take. Okay. So at least now for this f, for this w, the torque will be r cross w. But what is the distance? This r is the distance between the axis of rotation and where the force applied. So axis of rotation is also at this point, through this point, and the force also, weight is also at this point. So r is 0. So at O, the torque will be 0 because here r is equals to 0. Okay. Now at this point and at this point, so as a rotational equilibrium, so what is the students direction of rotation due to this force? So this force, anywhere the force on this side from this axis of rotation, so it will rotate it in this direction, and the on this side from axis to this point, any force from between these 2 points will, if it is in upward direction, so it will rotate it upwards. So due to T2, this will be your rotation. So this is your positive direction, this is your negative direction. So it's your choice. Now, so this is the rotational equilibrium. We will write the torque at this point and at this point. So you can write it in the same way also, like this way also, like the torque in clockwise direction is equal to torque in anti-clockwise direction. Okay, so adding up all the torques here which are in clockwise direction and here in anti-clockwise direction, or you can write it in the same way. First, the one which are in anti-clockwise, write them positive, and one which are in the clockwise direction has negative sign, and then equals to 0. So here again you have both the choices. So let us start with this choice. Sigma torque is 0. So you can start with, you can take any of the choices, that's your choice. So this distance, you know that this distance is total 2 meters. So what we can do, instead of taking these two variables, actually this is 2 and this is given as d, so this will be d minus 2, right? Sorry, 2 minus d. Total length is 2 and you are subtracting d out of 2, so this will be d minus 2. So this length will be d minus 2 and this length will be d. So d and d minus 2.
So 2 minus 2.
Sorry, again I have written, that's 2 minus d. So total is 2, subtracting d out of it, 2 minus 2. Okay, so now this again, if we take this net torque, that is r perpendicular into f, we will be taking. So this is your T1 and that's your O, this is your D. So what will be r perpendicular? So this is a line of action, so the distance between this and line of action, right? So this is your r perpendicular. Okay, distance between the axis of rotation and the line of action. Yes, this. So what is this angle here? So we need to find this angle. So this angle, you can see here from the figure that this was my T1. So this was my angle theta. So what is this angle here? This angle is, this is 90 degree. So total is 180. So sum of these two angles is 90. So this angle will be 90 minus theta. Okay. So this angle is 90 minus theta. So what will be this opposite side? Opposite side is equal to hypotenuse sine theta. So hypotenuse here is this angle is 90 degrees. So hypotenuse is your d. So this r perpendicular is equals to d sine theta, which is your opposite side. So theta here is 90 minus theta. So this will become d cos theta. Okay? Yes? Shall I tell it again or is it okay? Students, this was your T1. You can see here, this is your T1 and this direction here is along with the vertical, it's theta. Okay, and this is your rod, this is point O, this distance is D, and this is the force acting on it, T1. Okay, so this is the line of action. Okay, and we have to draw the perpendicular from O on this line of action. This is the perpendicular distance. So this we need to multiply with T1. So this tau is R perpendicular into T1. Okay, and the direction is positive direction. Okay, and but what is this R perpendicular? This we need to write here. So let us find this R perpendicular. So this angle is theta. So this angle is 90 degree. So what will be this angle? So this is a straight line, 180 degree linear pair. This angle is 90. So sum of these two angles will be 90. So this angle will be 90 minus theta. So that's your 90 degrees. So this is your hypotenuse here. Okay, and this side is this side is your opposite side, right? This is adjacent side, this side, and this is your opposite side to this angle. So opposite side is equals to hypotenuse sine theta. So hypotenuse is D, so D sine theta. So what is theta here? Theta is 90 minus theta, right? So that will be equals to D cos theta. Is this clear? So this is D cos theta into T1. Okay, students. Now, so this direction was this direction is clockwise. So clockwise directions are negative. So this direction will be negative. Now due to T2 plus, so this direction is plus. So similarly here also we can find, students. So if you want me to draw it again, this is O, this is T2. So again the angle with the vertical here, we have assumed it as alpha, and here this is the same figure as this one. This is the same figure as this one. Okay. So this is your line of action, and this is your from axis of rotation to line of action. This is your R perpendicular here in this case, and this so this is R perpendicular means into T2. So what is R perpendicular? So this angle is phi. Again this is 90. This angle is again 90 minus phi. So this opposite side. So this magnitude is 2 minus D. This side, which is your hypotenuse. So hypotenuse 2 minus D into, this is opposite side. So cos 90 minus phi. So what is cos 90 minus phi? Cos 90 minus phi is sin phi. So sorry, this opposite is hypotenuse sin theta, students. This is, what is this R perpendicular? So this R perpendicular will be equals to, opposite side is equals to hypotenuse sin theta. So this is opposite to this angle is 90 minus phi. So this R perpendicular, this distance will be equal to, this is a line of action where force is applied, and this is your axis. So distance between the axis and line of action is your R perpendicular. So this opposite side is equals to, hypotenuse is 2 minus D into the sine of 90 minus phi, and that opposite side will be equals to 2 minus D into sine 90 minus phi is your cos phi. So that's your R perpendicular in this case, 2 minus D cos phi. So here the direction is it will rotate it in this direction, anti-clockwise, that is positive direction. So plus net torque is 0, so plus 2 minus D into cos phi into, so that's R perpendicular into the force, that is T2, and the net is 0. So this was in this direction, that is negative direction, and this is in positive direction. Okay, so you can write it like clockwise is equal to anti-clockwise. So this negative will become positive. Okay, so we'll get T1 cos theta into d is equals to so this has become gone this side, so become positive. I'm writing this side here, and you can write this side over here. So 2 minus d cos phi t2, you can write, if here you are writing t1, so t2 2 minus d cos phi, so this into 2 minus d. So you can, in the same manner we can write as we have written the left hand side, t2 cos phi 2 minus d. Okay, so students, these are my two equations. This is so which equations? So this equations contains w, so I'm not going to engage this equation. So this equation t2 sine phi, t1 sine theta. So if I take these two equations and dividing them out, so this is dividing it with this side, t1 sine theta, and this t2 sine phi. So you can see that t1 gets cancelled out, t2 gets cancelled out. We know the value of theta and phi. Okay, so cos upon sine is cot, so cot theta into d is equals to cot phi into 2 minus d. Okay, and that we can further write as this is see, you can see here that this theta is 36 see, theta is 36.9 and this is 53. So what is the sum? 36.9 and 53.1. So the total is 90. It means that theta is equals to 90 minus phi. Okay, or we can write phi as 90 minus theta, so that's the same thing. Okay, so students, we can write here, this is cos theta d, so we can write this cos phi as this phi as 90 minus theta into 2 minus d, right? So this is cot, this is cot, so this is cot theta into, so d cot theta into 2 minus d, write it in the beginning. So cot 90 minus theta is your tan theta. Okay, cot 90 minus theta is your tan theta, right? So what is cot theta? Cot theta is equals to, so this become tan square theta, or so we know the value of 36.9 actually. So cot tan 36.9, so let us assume this value is given to you, that is equals to 3 upon 4. So what is cot 36.9 equals to? Four by 3.
4 by 3.
So this cot we can write as so as you see that we have written the theta as 36.9, so cot 36.9 will be 4 by 3 and 2 minus d into tan theta is 3 upon 4. So students, you can find it out and you will find that t is equals to 0.72 meters, so that is 72 centimeter. So means this distance from the right is This distance is 0.72 because the road was non-uniform. So students, now you can do the question 7.9 exercise question all by yourself. So it is taking so much of the time because I have so much of the diversified group. Some of the students are taking this is their first class of this chapter. Some of the students have taken other classes, some of the students have skipped last class. So I have so much of the diversified group, and I want you to be comfortable. Each and every student should understand. So that is why it is taking so much of time getting the whole thing revised, and then but still I hope that it is beneficial for everyone. Thank you so much. We'll meet tomorrow at same time.